Yay, this morning we get to do a projectile motion question. What a treat. So a ball is projected from the ground level at an initial speed of 30 meters. So initial speed equals 30 meters per second at an angle of 36 degrees above the horizon. So if I start to think about this as a diagram, here's my horizon. That's the vector that is going at 30 meters per second. And there's an angle of 36 degrees in there. Use your knowledge of vector calculus to model the motion of the ball. Use this model to determine whether the ball will clear a 10-meter high vertical wall that is 70 meters horizontally away from its point of projection. Assume the effect of air resistance is negligible and the acceleration due to gravity is 9.8 meters per second. So first thing that we're going to do is we're going to talk about this little diagram here. Now, this little diagram is going to help us work out what our displacement is in terms of velocity in our I and J component. Currently, we've got it going like this. Our vector for the initial speed goes at 30 meters per second at 36 degrees. So we're going to break it down into I and J components. So if I think about this as being a right angle triangle, this component down here is going to be 30 cos 36 degrees in the I direction, and this one over this side is going to be 30 sine 36 degrees in the J direction. Now, I need to notice that this is in degrees, not in radians. So our calculators would need to be changed into degrees to make this question work. So once you do that, now I'm going to chug and plug this into the calculator. You could be using exact values, so I could go forward with these calculations, but because this is tech active, I don't have to. So that one there will become 17.63 in the J direction. And this one down here is going to be a whopping 24.27 in the I direction. So even though this thing has an initial speed of 30 meters per second, because it's going off at an angle, I could measure that as it's actually moving at 24.27 meters per second in the I direction. So if you're measuring it as going this way, that's how quick it's going. Okay, so now we can start to calculate our vectors for the motion of the ball. So always, initially, when we start with looking at projectile motion, one of the conditions is that gravity is the only force acting on this thing. So we're going to start with gravity being negative 9.8, and gravity is the thing that pulls you back down to Earth, so that's in the J direction. Next thing we're going to do is we're going to integrate this, and we're going to account for our velocity. So the next function that we're looking for is going to have, this is the only thing acting in the I direction, so it's going to be 24.27 I. Like I said before, I could write this if I wanted to, but I don't have to. Plus, bracket, this is acting in the J direction, because that's the thing that's making it go up. Now, it has a force working against it too. Okay, because we also have to account for the acceleration, which is pulling it back down to the Earth. Now, we can't just chuck on minus 9.8 there, because this is an acceleration amount, and we want the velocity amount for it. So if I integrate this, integrate this, then I'm going to get minus 9.8 t in the J direction. Okay, and now I've accounted for the force that's going up and the force that would be dragging it down. So now I've collected all of my forces. This is my function for that thing. Last thing we're going to do is we are going to not do that. I'm on a roll this morning. RT. So we're going to integrate this function to find out what our displacement or our position vector is. So that's just going to be 24.27 T I plus 17.63 T minus, now when I integrate this one, the T is going to become squared, and normally that would divide this bottom by 2, meaning that that front number, when I halve it, will become minus 4.9. Okay, so now I have my x component, which is this one, and my y component. Now, I did forget my bracket there and my j. Okay, so now we've got all of our different formulas that we'd want to model the motion of this ball. The next thing we're going to do is we're going to test this statement here. So if we've got a 10-meter high vertical wall, that means that we can solve for our time when t is equal to 10. So all I have to do, let x equal, 70 is the vertical displacement. So if I draw this as a diagram, we're saying we threw a projectile. Your wall over here is 10 meters tall and you are 70 meters away. So we're going to let x equal 70 and find out what time that occurs. So 70 equals 24.27 t. Take this over by division. T equals 70 divided by 24.27. And you get t is equal to 2.88 seconds. So it takes me 2.88 seconds to travel that far. Okay, now the next thing is the thing that's going to tell us whether this statement is true or not. So if I want to then assume, so we're going to let t equal 2.88, and that's going to tell us the vertical height of the ball we're at that time. So if it's anything over 10, wham bam, thank you ma'am, we're on to a winner. But if it's anything below 10, then kaboom, we're going to hit the wall. Okay, so, and we're substituting this into our y1. So y equals 17.63 times 2.88 minus 4.9 times 2.88 squared. Now, when you chuck that into your calculator, you'll end up with 10.13. So, therefore, yes, this will make it over the wall. But only just, you're only just going to clear it by about 13 centimetres. So that's about a hand high. So it's not great clearance, you're going to be pretty close.